Have you ever just stood on a street corner, craned your neck back, and looked up at a giant skyscraper and wondered, how? Seriously, how does that thing stay up? Well, today we're going to peel back the layers of glass and steel and look at the secret skeletons, the incredible engineering hidden inside that make these giants possible. Let's get into it. I mean, that's really the million-dollar question, isn't it? It's not just about defying gravity, it's about not getting knocked over by the wind. And the answer is just this amazing story of human ingenuity, a constant battle against the forces of nature. You have to understand, from the moment it's conceived, every single skyscraper is designed for a fight. It's built to withstand a relentless assault from some of the most powerful forces on Earth. So, engineers are basically dealing with two main enemies. On one hand, you've got gravity loads. This is the constant, totally predictable downward pull of the building's own weight, we call that the dead load, plus all the stuff inside, like us, furniture, you name it. That's the live load. But the real challenge, the thing that keeps engineers up at night, is the fight against lateral loads. These are the chaotic, unpredictable forces that push a building from the side, like wind and earthquakes. Think of wind as this relentless bully that gets way stronger the taller you are. It's constantly pushing on the building's face, its facade. And we're not talking about a gentle breeze here. This wind load gets exponentially stronger the higher up you go, basically turning the top of a skyscraper into a non-stop battleground. Now, earthquakes, they're a completely different kind of monster. They don't push from the side, they attack from the ground up. An earthquake shakes the very foundation, creating this massive inertial force that just ripples through the entire structure. It all comes down to that classic physics equation, right? Force equals mass times acceleration. And here is the absolute paradox for engineers. When you're fighting an earthquake, the building's own massive weight, that dead load, suddenly becomes your worst enemy. Because of that F equals M times A formula, the more mass, the more M a building has, well, the more force an earthquake can slam into it. It's a totally counterintuitive problem, and solving it is genius. So, okay, we know the enemies. How in the world did we start fighting back? Well, the first solutions were all about creating these incredibly strong internal skeletons that let us get off the ground and start building what we'd call mid-rise buildings. The name of the game, the number one goal, is to control something called drift. That's just the fancy engineering term for how much a building sways from side to side. See, a little sway is okay, but too much drift, the building gets unstable, windows can literally pop out, and yeah, everyone inside would get incredibly motion sick. So limiting drift is everything. So early on, the go-to was the rigid frame, just a straightforward skeleton of beams and columns. It worked great for buildings up to, say, 20 stories. But to go higher, engineers brought in shear walls. These are massive, solid concrete walls, usually built around the elevator core, and they act like a powerful spine for the building. Then, of course, they figured, hey, why not combine them? That gave us the wall-frame interaction system, which got us up to about 40 stories. Each one was a huge leap. But let's be real, 40 stories is tall, but it's not a super tall skyscraper. To really conquer the sky, we needed a totally revolutionary idea. We had to rethink the building's skeleton from the ground up. And that big, revolutionary idea is captured perfectly in this quote. Instead of just having a skeleton on the inside, what if the entire building could act as its own structure? What if you could make the whole thing behave like a giant hollow tube? And that right there is the genius of the tube system. You space the exterior columns super close together, so close that the entire facade, the outer skin, becomes the main structural element. It's not an internal skeleton anymore, it's an exoskeleton, like on an insect. The original World Trade Center towers are probably the most famous example of just how strong and efficient this system is. Another really clever trick is the Outrigger system. Okay, picture this. If you're standing on one foot and trying not to fall over, what do? You stick your arms out, right? Well, that's exactly what this system does for a building. It uses these enormous beams, the outriggers, to connect the super strong central core to the outer columns, which makes the whole thing way more stable against tipping over. So we've figured out how to build up. But what about building out? Engineering these giants isn't just a vertical challenge. Now let's look at how engineers create those massive, wide-open spaces you see in stadiums or airports, without a single column in sight. There are basically three main plays in the playbook for spanning a huge void. You've got space frames, which are kind of like 3D trusses, perfect for big, square or round roofs. Then you've got cable-stayed or suspension structures, which use these incredibly strong steel cables under high tension to just hold everything up. And finally, you can use the power of shape itself with things called shells and folds.
And if you want to see this in the real world, just look at the absolutely stunning Signature Bridge in Delhi. It is a textbook example of a modern asymmetrical cable-stayed bridge. All those powerful steel cables are doing the heavy lifting, letting it stretch right across the river.
And for the sheer magic of shells, there is no better example than the Lotus Temple. This building's strength doesn't come from thick, heavy materials. No, it comes from its form. The elegant, curved shape of its concrete petals is what gives the whole thing its incredible structural integrity. It's where engineering becomes pure art. Okay, we have covered a ton of ground here, from forces pushing sideways to structures that stretch across giant voids. So to make sure this all sticks, let's connect the dots with a couple of quick questions. Let's test your knowledge. All right, think about it. You're the lead engineer. You're building a monster, 80+ stories tall. Your biggest enemy is the wind trying to topple it. Which system that we talked about are you going to choose as your most efficient weapon? If you said the tube system, you absolutely nailed it. By making the whole facade the structure, it turns the entire building into what engineers call a giant hollow cantilever. The easiest way to think of a cantilever is like a diving board. It's only supported at one end. The entire building is acting like a diving board anchored deep into the earth. It is unbelievably strong and efficient. Okay, let's do one more. We talked about those massive concrete walls, the ones usually tucked away around the elevator shafts. What is their main, number one job in a high-rise building? Yep, they are there specifically to carry those lateral loads. They are the building's spine. They provide that rock-solid core rigidity that's needed to fight back against the sideways push of the wind and the crazy shaking of an earthquake. So I'm going to leave you with this thought. These incredible structures, they aren't just glass and steel. They're a whole collection of brilliant solutions: spines, tubes, exoskeletons. The next time you look at a city skyline, I promise you, you won't just see buildings anymore. You'll see the invisible skeletons holding them all up against the sky. What story will they tell you?